Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying applications of first-order equations, specifically cooling and heating. We want to derive Newton's law of cooling. Suppose the temperature of an object at time little t is given by the function capital T, and the object is placed into a medium that has temperature T sub m. Notice that the object's temperature and the medium's temperature might be fluctuating. Newton's law of cooling states that the rate of change of our object's temperature is proportional to the difference between its temperature and that of the surrounding medium. Specifically, the derivative of T, the temperature of our object, is proportional, there's our constant K, to the difference between the temperature of our object and that of the medium, T minus T sub m. Now, why do we have a minus K rather than a K out in front? Ultimately, it's just a constant, it doesn't really matter. But if K is positive, then we have a minus K out in front. What this means is if T is larger than T sub m, if our object is hotter than the surrounding medium, then this parenthetical term of T minus T sub m is positive, and if K is positive, then this is now explicitly a negative number out here, meaning that T prime will be a negative times a positive overall negative. So if our object is warmer than the surrounding environment, the derivative of its temperature is negative, it will be cooling. On the other hand, if T is less than T sub m, if our object is cooler than the surrounding environment, then its derivative will be positive, it will be warming up. So here's the differential equation that we came up with. The change in the object's temperature is proportional to the difference between its temperature and that of the medium. Now the medium might also be changing temperature, so it will have its own differential equation where its derivative is proportional to the difference between its temperature and that of the object. Now these constants, K and K2, are presumably different from one another. They represent material properties of the objects, and since your object and the medium you're placing it into are presumably different materials, these will be different constants. However, this gives us two differential equations that interact with one another, because the derivative of T will change the value of T, which will change the derivative of Tm, which will change the value of T prime, and these feed into one another. So we have two differential equations that affect one another. This is a system of differential equations. We're not prepared to solve such systems yet. So for now, we're going to presume that the surrounding medium, Tm, is a constant temperature. It's not changing. So Tm is now just a constant. So here's our differential equation where Tm is now just a constant. So the only thing that's changing is the temperature of the object, capital T. Now this assumption is actually relatively accurate when the medium has a much larger heat capacity than that of the object. Like you might be throwing a single hot stone into a swimming pool full of circulating water or something like that. Or maybe the environment's temperature is being actively maintained. Okay? An oven maintains an internal temperature, an air-conditioned room might maintain a relatively constant temperature, and so forth. With Tm just a constant, however, we now have a separable differential equation, so we can solve it. So here is our differential equation where Tm is a constant. This is separable, divide T minus Tm. Now you've got all of your T's and T primes on one side with none of them on the other. We can integrate both sides. We have the log of the absolute value of T minus Tm is minus Kt plus some constant. We now exponentiate, and as we've done several times, e to a constant comes out as a constant scalar, and we call that capital A. And this means that T minus Tm is plus or minus some constant times e to the minus Kt. Moving the Tm to the other side, the temperature of our object is equal to the temperature of the surrounding medium plus or minus some constant times e to the minus Kt, where K is some constant that represents the material we're working with, and T is the variable for time. So here's our solution. T is the temperature of the surrounding medium plus or minus some constant times e to the minus Kt. Now what was that constant A? A was e to something in the previous slide, and e to something is definitely positive. So capital A in the line we have right now must be a positive constant, but we do have a plus or minus in front of it. So A is an arbitrary positive constant with a plus or minus. If we simply replace that in our minds with A being an arbitrary number, positive or negative, then the plus or minus can be dropped. So now we understand that capital A could itself be a negative constant, and we don't need the plus or minus. So capital A might be positive, might be negative at this point, but we don't need the ambiguity of the plus or minus sign. Now let's put some initial conditions in here. If I let t equal 0, well then here we get a 1, so this becomes just A, and T sub 0 is going to be our initial temperature. So T sub 0 equals Tm plus A allows us to solve for A is T0 minus Tm. In other words, A is the difference between the initial temperature of our object and that of the surrounding medium. We plug that in, and here is the solution that we get. The temperature of our object at time t is that of the surrounding medium plus the initial difference between its temperature and that of the medium times this exponential term. And here is the formula that many of us are used to working with from our pre-calculus classes for Newton's law of cooling. But what about a system where heat is actively being generated or removed? In our previous derivation of Newton's law, the only energy transfer that's happening is passive, so to speak. Our object is placed into a medium, and the temperature change reflects a flow of energy from the object to the medium or vice versa. But what if the object is itself generating heat at some sort of constant rate? Like I might have a radioactive substance that I'm putting into a cooling bath. I'm relying on energy being transferred from the object to the cooling bath, but the object is generating its own energy simultaneously. So can we determine the long-term temperature of an object in such a system? Well, this actually looks quite similar to something we studied in the previous video. So here we have two terms in our differential equation. K1 is a constant that represents how energy flows between the object and the surrounding medium. K2, on the other hand, represents the constant rate at which energy is being added or subtracted from our object. This is, however, an equation we've already solved. So now we're interested in solving this differential equation, where the derivative of the temperature is proportional to some constant times this difference with an extra constant added in. But this is exactly analogous to something we've already studied, population growth, which is proportional to the size of the population with an added constant external factor. Notice this is really exactly the same thing. Here we had a K1, here we have a minus K1, but they are just constants, that doesn't really matter. Here we have our added constant K2, that's exactly the same between the two situations. And instead of just having A prime being proportional to A, we now have T prime being proportional to T minus Tm. But since Tm is just a constant, T minus Tm is not terribly different than just T. So we can solve this with the same techniques that we used in the previous video. And we're going to end up with a pretty similar solution. We're not going to go through all the work of doing it again. Here's what you'll get. Compare this to Newton's law of cooling, and you'll see it's actually quite similar. In Newton's law of cooling, this K2 over K1 is not present, nor is this one. But that's really the only change between the two solutions. But what happens as t goes to infinity with our new solution here? Well, K1, remember, was positive. So e to the negative K1t goes to 0, and this entire term drops out. So as t goes to infinity, there is a constant solution of the temperature of our object is that of the medium plus K2 over K1. Now let's return to the problem of thinking, what happens if the temperature of the medium is fluctuating? So let's go back to the simple cooling equation where the derivative of the object's temperature is proportional to the difference between its temperature and that of the medium. Okay, so there's no constant heat generation term being added here. Now we already noted that if the temperature of the medium also depends on T, we end up with a system of differential equations, and we don't yet know how to solve that. But it's possible to consider the temperature of the medium changing, but not in a way that depends on the object's temperature. For example, the temperature of the medium could just fluctuate sinusoidally. So the temperature of the medium could be given by a function like this, which only depends on T, the time. It's not actually dependent on the temperature of the object, capital T. So this is a situation where the temperature of the medium is changing, but not actually in a way that depends on the object's temperature. It depends only on time. So in general, if we change our assumptions about the explicit function t sub m, we get very different differential equations. So here's the differential equation we set up, but now t sub m depends on t, time. What it doesn't depend on is capital T, the temperature of the object. In general, however, you would distribute this out and rearrange to get the following nice, clear, linear first-order differential equation. We have capital T prime plus a constant times capital T equals, and on the right we get some function of lowercase t, some function of time. So the temperature of the medium times some constant becomes our forcing function. Now the complementary equation, where you replace that forcing function with 0, is always going to be solved by e to the minus kt. And recall, in our previous solutions, we kept getting an e to the minus kt in our solutions. That's because it is the solution to the complementary equation we get here, where you replace this forcing function with just a 0. But if I change that forcing function and I put it back in to find a particular solution to the inhomogeneous equation, it's very much going to depend on what I make t sub m equal to. If I replace it with something constant, then finding a single solution to the inhomogeneous equation isn't very hard. But if I replace it with a very complicated function, the problem might get very difficult. Overall, what have we learned? We set up Newton's law of cooling and solved it as a first-order linear differential equation to generate a formula that many of us have seen before. Now we can also modify our initial differential equation in a few ways, like adding constant heat generation from the object, and we were able to solve that as well. If you want to account for a fluctuating temperature of the medium, as long as it doesn't actually depend on the object's temperature, but simply only on time, you end up with a forcing function in a linear first-order differential equation. Finding a solution to the complementary equation is pretty easy, but depending on the forcing function you pick, variation of parameters will be needed to solve for a particular inhomogeneous solution, and that might be very difficult depending on what forcing function you pick.